All right, in the last video, I derived the vorticity equation, which is essentially done by taking the curl, which is a calculus vector identity of the momentum equation, and through a bunch of calculus identities, essentially found an equation for how vorticity, the amount of spinning, changes in time. Now we're going to do the same thing, but for divergence in a more consolidated way, and that tells us how much air enters or exits a region from all sides. So again, we start with the same kind of thing from the last video. If you're not sure about these two, you can check the last video, but this is a way to write the momentum equation. This is the momentum equation. So I'll write that out. Momentum, as in like velocity, that kind of thing. Velocity equation, momentum equation, same kind of thing. So are the same thing. This is still friction and Coriolis term. Now we take the divergence of both sides instead. So we can define divergence as d, for example, whatever. The derivative can come out, and then the divergence will come in. So it will be like, divergence of v on the inside, d dt, which is divergence. So that term is taken care of. And let me check something. So from the past, okay, yeah, so there's a slight mistake. So this is actually not the total derivative, it is the partial derivative. So I think that means that the equation is already Eulerian. So okay, so that's the partial derivative, not the total derivative, because we've already taken advection out. And so we have this term, we take the divergence of that. If you remember, divergence of gradient is just shorthand. We define it as, gradient squared. Del squared, not gradient. But so we just apply this to both terms. We have a Laplacian of this term. Now, this term is only in the vertical equation. So when we apply the Laplacian, we'll only get the vertical derivative out, and all terms like ik will cancel, jk will cancel, and then we'll be left with k dot k, which is equal to 1. So this won't be a vector anymore. This is a vector, but the divergence of a vector is a scalar. Now, since this term is equal to gravity times z, or you can say negative gravity times z, however you define g, the sign of g, if g is a constant, we assume g is 9.81 or something, then this is 0. But actually, gravity does change with height. So this is actually a function of z. We usually assume it's 9.81, but that's not true. It actually varies. I think it's like 0.2 or something. But if we assume it's not varying, like if we don't do any assumption, it will be z times the vertical gradient of g, where this is just a shorthand for this, plus 2 times a single derivative of g. So that's interesting. This term here, you use a vector identity, so it's v vector dot the curl of a non-inertial vorticity, where this is equal, from the last video, this is equal to omega, is equal to omega plus 2, also omega, different capital omega vector, where this is equal to some, I think it's like cosine phi j plus sine phi k, and then omega is equal to the curl of velocity. And then so you have another term, which is initial vorticity of the non-inertial vorticity vector dotted with the curl, which is also called omega. This term you'll have kind of like the last term where there's a cross. It will be the same, but it'll be a dot. And I believe you might want to check me on this one. I think it will make a term like this, and that is called, I guess I also called it variclinic generation, but it might not necessarily be called that. But similar to the last term, it's kind of that kind of variclinic term. And then you also have alpha, which is 1 over rho, which is density, times the Laplacian of pressure. Laplacian, I believe it has to do, like, if you have a peak in the pressure, in a distribution of pressure, maybe pressure in X or something, it will tend to make the peak more flat, essentially. So it's kind of like, if you do that to the Laplacian of velocity, it acts as friction. So here you can, I guess, kind of see is essentially damping pressure. And then as for this term, while in the case of curl, which is has an when you make the equation like A cross B, it's A B sine. So it's the strongest when the angle between these two elements, the density and pressure gradients, are 90 degrees to each other. But this one, since it's a dot product, it happens when the angle is 0. So if you have two gradient fields, one for pressure, maybe you have a gradient going this way, and then you have the same thing overlaying with it, but for alpha, and then the gradient also goes the same way. So if the gradient goes the same way, it's the strongest when they're the same. So that would mean that if these are the same, then divergence should be increasing the most, because if you go to this side of the equation, that's what, if you go to this side of the equation, or here's the whole thing written down here, if you go to this side of the equation, this term will, I see. This term will be on the right-hand side, so it will be negative. So this will mean that if these two are in the same direction, it will be decreasing divergence. So it could eventually lead to convergence. But yeah, that's a bit of a complicated equation. It's hard to kind of read everything and understand what's going on. But as long as you can do the calculation, you'll know what's happening with divergence, and you can see whether air is converging or diverging from a region. But it is a very, I guess, important equation to have, I guess, in your toolkit, or know of its existence. Maybe you won't use this because you'll just calculate U and V and W, or what I said was Vx, Vy, Vz separately, and then you just calculate the divergence term, which is dVx dx plus dVy dz. Maybe you just calculate them separately with the momentum equation, which is here, and then you don't even need to know this. But it is very nice to know that what is the fundamental things that are causing divergence to change, and it would be these terms. Maybe some other terms that were too complicated for us to look at, or to fill into, like, to write out. So, which is Coriolis and friction. So, thank you for watching this video, and if you haven't seen the last one on vorticity, go check that out as well. All right, thank you. Bye bye.